Hey everyone, welcome back to Linear Algebra. This will be lecture 18 of the course, and in this section we're going to discuss various methods for simplifying bases, identifying bases, building bases, etc. So let's go ahead and jump into it. We'll call this section 4.6, Constructing Special Bases. Okay, so let's go ahead and start with an example. Okay, we'll start with a nice example. Let's let S equal the set 2, -2, 3, 5, 5, and then -1, 1, 4, 14, -8, and 4, -4, -2, -14, and 18, and 3, -3, -1, -9, 13. Okay, so we've got this set of 4 vectors from R5. Okay, and so the vector space that we're going to be interested is the span of this set S. So we're going to let V equal the span of S. Okay. And now what we want to do is we want to identify a basis for this vector space. Can we identify a basis for V? Okay, now S is certainly a spanning set, obviously, because the vector space V is equal to the span of these 4 vectors. Now, it may or may not be linearly independent, but it is spanning, right? So one way to identify a basis would be to just start removing vectors from S that are linearly dependent. Right, and so we could spend some time trying to do that. There's a lot of guess and check. There may be other methods that you could employ to kind of do it more systematically. But one quick way to identify a basis given a set of vectors like this, and a vector space that's equal to the span of this set of vectors, is to use the row space of a test matrix. So we can identify a basis by using the row space of a test matrix. Okay, kind of like what we did previously, where we would go and identify the spanning set using the row space of a test matrix. We're going to do the same kind of thing here. So we're going to take the elements of S and we're going to plug it into a test matrix as the rows, not the columns. Okay, so we'll say 2, -2, 3, 5, 5 is the first row, -1, 1, 4, 14, -8 is the second row, 4, -4, -2, -14, 18 is the third row, and then 3, -3, -1, -9, 13 for the final row. Okay. And so we know that this is, when we talk about the reach of the rows of a matrix, we're talking about the row space. And we know that when we row reduce a matrix, the row space stays the same, right? And so let's do that to this matrix. Pause the video and see if you can put this into reduced row echelon form. And once you do that, you should see 1, -1, 0, -2, 4, and then 0, 0, 1, 3, -1, and then 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so the row space of this reduced matrix over here is equivalent to the row space of this original matrix. And what does that mean? Well, what that means then is that these 2 rows of this reduced row echelon form matrix are a basis for the vector space equal to the span of the 4 rows of the original matrix. Okay, so the set B equal to 1, -1, 0, -2, 4, and 0, 0, 1, 3, -1 form a basis for V equal to the span of S. Okay. Right, we can see that V has dimension 2. right? V has dimension 2 because we found a basis for V, and it has 2 vectors in it, meaning, and then we know that all bases have the same number of elements in them. Right, so in general, this method of simplifying a basis works. Why does it work? It works because a reduced row echelon form matrix, right, like this guy right here, a reduced row echelon form matrix like this, it's going to have the simplest form of all the, infinitely many matrices that are row equivalent to it. Right, so this is one particular matrix that is row equivalent to this reduced row echelon form matrix. There are obviously infinitely many, but this is going to be, in general, the simplest form of the row space for a matrix. Once we put it into reduced row echelon form, it becomes the simplest form of the row space. Okay, and so through this, using this method, we can start with the spanning set, and this effectively reduces the spanning set down to 2 vectors that are the simplest, meaning the smallest numbers, in form to the original. Okay, and so we can actually take this method and it can be adapted to suit other vector spaces than Rn. So let's see another example where we do that. So let's think about polynomials, for example. Let's let S, another example, let's let S equal polynomial space x squared minus 3x plus 5. And I'm going to write on a separate line just so we can see clearly. 3x cubed plus 4x minus 8. And then 6x cubed minus x squared plus 11x minus 21. And then finally, 2x to the 5th minus 7x cubed plus 5x. Okay, so this is a set S of 4 polynomials, and S would be a subset of P5, 5th degree or less polynomials. Now, obviously, we don't want to work with polynomials like this, so we can represent these polynomials as 6 vectors whose entries are the coefficients of these polynomials, right? So we can rewrite S as a set of vectors, right? So for example, the first one we could write as 0, 0, 0, and then 1, negative 3, 5, 1, negative 3, 5. Okay, so we just write it as a vector. And then 0, 0, 3, 0, 4, negative 8. Okay. And then 0, 0, 6, negative 1, 11, and negative 21. And then 2, 0, negative 7, 0, 5, 0. Okay, so this is another way to represent these polynomials. Okay, and we can apply that same trick to this set S, right? So if here we're interested in finding a basis for the span of this set, okay, we want to find a basis for the span of S, we can use that exact same trick, and we can plug these guys into the rows of a matrix. So 0, 0, 0, 1, negative 3, 5, 0, 0, 3, 0, 4, negative 8, 0, 0, 6, negative 1, 11, negative 21, and then 2, 0, negative 7, 0, 5, 0. We can row reduce, so again, pause the video, make sure you know how to do the row reduction. I'm skipping over it, but you'd get 1, 0, 0, 0, and then 43 over 6, and negative 28 over 3, and then 0, 0, 1, 0, 4 thirds, and negative 8 thirds, and then 0, 0, 0, 1, negative 3, and 5, and then the last row does drop out, and you get all zeros. And so we could take this as the basis for our spanning set. Okay, and then we could translate this back into polynomials if we like. So we could write this as x to the 5th plus 43 over 6x minus 28 over 3. It's the first line. The second polynomial would be x cubed plus 4/3 x minus 8/3. And then the last polynomial would be x squared minus 3x plus 5. Okay, and this would be a basis for the span of this original set of 1, 2, 3, 4 polynomials. Right? You can see that one of those polynomials was redundant. Right? And so we've actually been able to get rid of it and further simplify it. And then we can obviously see that the dimension of V is 3 in this case. There's 3 polynomials required to span it. Okay. And so this is just a couple of examples of how starting from a set in a vector space, which is equivalent to the span of the set, you can reduce the spanning set, to just the essential vectors and actually simplified versions of the essential vectors. Okay, very good. All right, so sometimes we may be interested in reducing the spanning set by eliminating the redundant vectors, but still retaining some of the original vectors. Okay, so sometimes we may want to keep and I'm just going to write non-redundant vectors from the original set. Right. So in the previous examples, we didn't retain any of the old vectors, the original vectors. We just found new vectors that were equivalent and got rid of the redundancies. And so what we may want to do is, hey, maybe we start with a very specific set and we want to just toss out all of the redundant vectors but keep the originals. Okay. Okay. And so this brings up a theorem. Okay. If S is a spanning set, if S is a spanning set for a finite dimensional vector space V, okay, then there is a set B, a subset of S, could be equivalent, it's a subset, possibly equal to S. There's a set B in S that is a basis for V. Okay, so all this means is, hey, if I start with a spanning set, it is indeed possible to potentially just remove a handful of those and get down to a basis. I don't necessarily have to change any of the vectors. I can just dump them and basically arrive at a basis. Okay, so let's see an example of this. Okay, let's see an example of this. Let's let S equal 1, 3, negative 2, 2, 1, 4, 0, 5, negative 8, and 1, negative 7, 14. Okay. And let's let V equal the span of S, right? So the vector space of interest is the span of S. Well, so some small amount of work may be required. You may have to look at these vectors for a minute, but it is possible to confirm that 2 of these are linear combinations of the other 2. So we can confirm with some work that, so specifically 0, 5, negative 8, that vector there, that can be written as 2 times 1, 3, negative 2 plus negative 1 times 2, 1, 4. Okay, so these two vectors here can be used to write the third. And additionally, we can see that this last vector is a similar situation. So 1, negative 7, 14 can be written as negative 3 times 1, 3, negative 2 plus 2 times 2, 1, 4. Okay. These other two vectors are linearly independent. These two are dependent. These first two are independent, right? And so a basis for V equal the span of S is basically these first two vectors. So 1, 3, negative 2, and 2, 1, 4. Okay. Right, and so this is just an introductory example. So in general, right, the idea here to retain a basis subset for a set S, we basically need to identify a maximally linear independent subset of S, right? We need to reduce the set S by throwing out any dependent vectors. Okay. Okay. Let's do another example. Take a look at another example here. Let's let S equal the same set, and we'll talk about how else we could do this, how else we might accomplish this. Okay, so we've got this set of 4 vectors, the same as the previous example. Now, it's obviously easy if I just tell you which ones are linearly dependent, right? But it's not always so easy in practice to figure out which I should keep, which I should throw away, right? Especially by brute force, just by guess and check, right? So we need to identify which vectors are linearly dependent. Now what we can do, we've done this before, is we can take these vectors and we can put them into a test matrix as the columns of the matrix. So we can put these vectors into a test matrix as the columns. Right? So if you recall, we had a test for linear independence. We would put all of the elements of interest into the columns of a matrix, and we would row reduce. Okay, and so let's do that here and see what we get. So 1, 3, negative 2, 2, 1, 4, 0, 5, negative 8, 1, negative 7, 14. Okay, we can row reduce this. And we get 1, 2, 0, 1, and then 0, 1, negative 1, 2, and then all zeros after that. Okay, and so what we're interested in is what we're looking for are which columns have a pivot. Right, so we've got a pivot here in column 1. We got another pivot here in column 2. You'll notice there's no pivot in column 3, no pivot in column 4. So pivots are in columns 1 and 2. What that tells us is that the vectors that we plugged into columns 1 and 2, namely these two right here, which correspond to, of course, these two vectors, those two columns, those two vectors are linearly independent. These columns, on the other hand, columns 3 and 4, they have no pivot. They point to the original columns of the matrix being linearly dependent. Right, so these get thrown out, and as we saw in the previous example, those do get thrown out. They can be written as linear combinations of the first two. Okay, so the third and fourth columns, what this basically implies is that the third and fourth columns can be tossed out, and a basis can be found using just the first two vectors. Okay, just like what we saw in the previous example. Okay. Right, and so we are able to reduce this spanning set to a basis. And what we found is that a maximally linear independent subset of S would consist of just these two vectors. Okay, very good. All right, now there's kind of like these two tests that we've been talking about. Let's kind of try to summarize these, or kind of draw out the key distinctions. So on the one hand, we had what we called the simplified span method. Okay, and this is of course where you plug the vectors in as the rows in a test matrix, and then you row reduce. That's the simplified span method. The other one is the independence test method. Dependence test method. Okay, so we had these two. Okay, now for the simplified span method here, what are we doing? We plug the vectors into the rows of a test matrix. Plug the vectors in as the rows of a test matrix. Okay. Now over here we're doing something similar, but instead of the rows, we're interested in the columns. So plug the vectors in as the columns of a test matrix. Okay. Now what does this tell us? What does the simplified span method tell us when we plug into as the rows of the matrix? Well, it tells us that what you're going to do is the rows that remain non-zero in the final matrix, the row reduced echelon form matrix, that's going to be your simplified basis. So creates a simplified basis using the rows of the RREF matrix. Okay. What happens over here? Well, this side over here, the basis is created as a subset of the original set, right? So this just tells us which vectors from the original set to keep. Okay, it tells us which vectors to keep. All right, so when we're done over here, we see, for example, up above here, we saw column 1 and column 2. Those are linearly independent. They're a maximally linear independent set. So we keep those two vectors and throw the rest out. Now notice this, you retain the vectors that you're given. Now that may or may not be a good thing. Sometimes you want the vectors that are given. Sometimes you want simpler vectors if they're available, right? It just sort of depends on your application. And then finally, obviously kind of to go along with this, the non-zero rows of this matrix are the new basis. Okay, and then over here, the pivot columns the pivot columns tell you which vectors to keep. Okay, so the pivot columns tell you which vectors to keep. So two totally different methods, right? One uses the row space, one uses the column space of a matrix. Both cases you row reduce, but your interpretation of the results are what varies. In one sense, you're saying, okay, here are the actual new basis vectors. In the other sense, you're saying, okay, go back to the original set and keep the ones that are linearly independent. Okay. Now, so those are kind of like the two, I would say, two of the kind of key things to hang on to. Now, sometimes it's easier to identify a spanning set by simply looking at the vector space, rather than by going through a whole row reduction mechanism, right? So sometimes a spanning set can be found by inspection. Okay, and so there's a method to this. There's a method to this. Here's the method in general. Here's how we might be able to do this. So we're going to let S be a finite set of vectors spanning a vector space V. Okay. The first thing we're going to want to do, right, is we're going to choose V1 that's non-zero from S. So we want to choose a vector, call it V1, that's not equal to the 0 vector from S. Okay. All right, so that's, I mean, you obviously just get started, basically, right? That's just the start. And now well, step 2 then, well, before I say that, we want to repeat step 2 as many times as possible. And what is step 2? Well, assuming you have some vectors chosen already, v1, v2, dot, 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 vk, assuming you've already chosen those, oh, sorry, k minus 1, we'll say, v1 through vk minus 1, assuming these have already been chosen, okay, from S. So assuming you've already chosen some vectors from S, we want to choose vk from S such that vk is not in the span of the previous already chosen vectors. Okay. Right, and so this is kind of a funny way to say this. I mean, what are we saying here, basically? We're just saying, hey, let's choose vectors that are not redundant. Okay, can we do that? If we can do that, then this is a very efficient way to do it, if we can easily tell if vectors are redundant. Right, and so sometimes that's the case. So let's see an example where that is definitely the case. Okay, let's let S equal the set 0, 0, 0, 2, 8, negative 12, negative 1, 4, negative 6, and 7, 2, 2. Okay, these are obviously a subset of R3. And the vector space of interest is the span of S. Okay, so let's choose V1. Let's start with the first step. So choose V1. It's got to be not equal to the 0 vector. Right? So let V1 equal 2, negative 8, negative 12, just the second vector in there. We might as well just choose any one we want, right? Okay. Okay, now that's step 1. So step 2, let's choose V2 in S such that V2 is not in the span of V1, right? We've only chosen the one vector so far. Now, if we've only got one vector in there, what is the span of that vector? Well, we basically just don't want any scalar multiples of V1, okay? And so let's look at some of these and see if any of these are scalar multiples. So let's see vector, well, obviously this is a scalar multiple, right? 0, 0, 0, I could just multiply this V1 by 0 and I get 0. This one's a scalar multiple. What about this one? Negative 1, 4, and negative 6. Well, note, negative 1, 4, negative 6 is actually equal to negative 1/2 of the chosen vector, 2, negative 8, negative 12. Right, so that's, you know, basically negative 1/2 of the chosen vector V1. So we don't want that. So that one can't be chosen. So let's choose 7, 2, 2. Is that one okay? Is that a scalar multiple of 2, 8, negative 12? That one is not. There's no way to turn a 2 into a 7 while simultaneously turning an 8 into a 2. Right? So definitely can't do that. So let V2 equal 7, 2, 2. Okay, so we can do that quickly. All right, and then so what about, can we keep going? Is there a V3 available? Well, this is our V1. This was not that this one was redundant. It's a multiple of V1. This is our V2. Right? This one we obviously say is a multiple of everything, so that one's out. So we're done, right? Then we can't go any further. There's no additional vector to choose. And so that means our basis in this case is something that we could identify from inspection as 2, 8, negative 12, and then 7, 2, 2. Okay. Okay, and so that's, in this case, it's probably quicker to just look at these vectors. You could rule out the first one and the third one pretty quickly. It might take 2 seconds to figure out that the third and fourth vectors were independent. Right? So this is one you could see pretty quickly. Okay. All right, very good. Let's keep plugging away, right? So we've got some different methods we're identifying for finding bases. Fact. Let's discuss this. We're going to talk this through here. So it turns out that every linearly independent set, okay, in a finite dimensional vector space is contained in some basis. This is a very interesting theorem. Okay, we're going to talk this through. Right, we'll state the theorem formally in a second, but let's talk this through. So let's let T equal the set T1 through Tk of vectors. And we're going to let T be a linearly independent set of vectors. A linearly independent set of vectors in a finite dimensional vector space V. Okay. Now, V, since it's finite dimensional, is going to have a finite basis. V has a finite basis. Let's call the basis A equals A1 through AN. So this is the basis for V. Now, consider the set of the union of T and A. Consider that union. So T union A clearly spans V. Why does it span V? Well, it spans V because A spans V. Okay, A spans V. So what we're trying to show here is that this arbitrary linearly independent set from this vector space V is part of some basis. Right? So if I say, okay, take T and join it, union it with a basis, an explicit basis that we know, then use that. What we can do is that we can use that alongside the independence test to identify which additional vectors we need to add to T1 through Tk to get to a basis. Now, how can we do that intelligently? How can we guarantee that T1 through Tk make it into the basis? Well, what we can do is we can order the columns of the test matrix with the T's first, so that they are guaranteed to stay in the basis, and that all of the A's we can put secondarily in there. Some of them will drop out, that's fine, but we will definitely retain the T's, right? So we want to set up a test matrix with t in front. And when I say front, you know what I mean, the leading columns. Right, so I've got my t1, t2, dot, 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 tk. Remember, these are linearly independent vectors. And I put them in the front of the matrix. And then on the back side of the matrix, sorry about this, I put a1, a2 through an. Now, this is a spanning set. We know that A alone, the columns of A alone, span the vector space. And we know that T1 through Tk are linearly independent. Now, when I row reduce this, what do I get? Well, I'm going to get 1, 0, 0, 0, something, 0, 1, 0, 0, 0, something, 0, 0, 1, 0, 0, and so on, right? And basically all of the first T rows are going to look like this, right? We're going to have a perfect identity matrix in the first T rows, right? And why is that? Well, T1 through Tk are linearly independent, so that's what happens. So these are the row reduced Tk vectors. Now, what happens over here is less clear. Some of these will have pivots, some will not. All of the ones with pivots we keep, and the rest, we maybe drop out. Okay, the rest will maybe drop out. So in this way, we can construct a basis that includes all of T and potentially some additional vectors from A. So remember, T is linearly independent. All we got to do is increase it so that it becomes a spanning set, and then we've got a basis. We might have to add a couple vectors to it. We don't know what those vectors are, but this is a surefire method to find them. Right? So if this has a pivot, it goes into the basis. If this one has a pivot, it goes into the basis. If these don't have pivots, then they're redundant. Throw them out. They're not part of the basis. Right? You just go until you find, you row reduce this, and it'll tell you exactly which ones you need for the basis. And it'll guarantee that the T vectors are included. Okay, and so that was just kind of a rough outline of a proof of how you might go about identifying a basis given a set of linearly independent vectors. So here's the theorem. So let's let T be a linearly independent subset of a finite dimensional vector space V. Okay. Then V has a basis. B with T is a subset of B. Now T may be the basis, but more likely T is a subset of the basis, right? T is going to be missing a few vectors. Okay, so let's see an example of this one. This is a very useful way to do things. Right, so consider the following. Linearly independent set. And this will be 2, 0, 4, negative 12, and 0, negative 1, negative 3, 9. And I'm going to call it T, actually, just because I want to mirror the previous demonstration. So this is a subset of R4. And we'll say R4 is the vector space of interest. We'll call R4V. Now, what we want to do is we want to find a basis for R4 that has these two vectors in it. Okay, so we want to use the previous method. So we want to end up with a basis that has these two vectors in it. Okay, so a known basis for R4 is, of course, E1, E2, E3, E4. And so we can use those together with T to construct our basis. So we set up a matrix A, and we plug in the columns of T first. So 2, 0, 4, negative 12. And then 0, negative 1, negative 3, and 9. And then we got to put in the vectors from the basis. So 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And now we're just going to row reduce this. Okay, and so I'll do that quickly. And when we do that, we get 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. And then we get negative 3/4, negative 1, 3/2, 0. And then 0, 0, 0, 1. And then negative 1/12, 0, 1/6, and 1/3. Okay, so this is what it looks like when we put it into reduced row echelon form. So where are my pivots? I got a pivot here, I got a pivot there. Naturally I would, these are linearly independent. I have a pivot here, so this column produces a pivot. These two are not non-pivot columns. Oh, sorry, this one is a non-pivot column. This one is a pivot, so let's circle the pivots. Pivot, 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 pivot. All right, so what does that tell me? Well, it tells me that a basis is going to be 2, 0, 4, negative 12, and 0, negative 1, negative 3, 9. That's my t, right? So t is a subset of the basis. The other vectors needed to form the basis are 1, 0, 0, 0. Right, we need this one. So these two obviously, and then the third over this one. And so then the other vector is 0, 0, 1, 0. Right? And so this is my basis, and you can see t is a subset of the basis. As desired. That's what we were after, right? Okay. All right, so now we know how to construct a basis. It should be no problem. We should have no problem constructing bases as needed as we go forward with the course. Things will come up later in the coming sections where we'll need to be able to quickly construct a basis, and we just need a couple of methods, techniques to do it. And so that's what this section was all about. Kind of a shorter section, but all about just here's a couple of techniques we can use to build up a basis quick, just using the theorems and the principles that we've learned about linear independence and spanning sets. Okay, so I'll go ahead and leave it there, and we will see you all in the next lecture. Take care.